So I'm Paris. For those who I haven't met before, I've been doing research on distributed computing, and I've been a Flink committer for a while, especially in the early days where we had to take big decisions about state and fault tolerance. But today I'm going to speak about something completely different. That's the idea of incorporating streamed loops on Flink. It's a project that we've been working on for a year or two, and I think by now we have some interesting findings that some of you will find very interesting. I'll do something similar that Kostas did in the keynote today. So I will play some big landmarks in stream compute technology and see where we are today. So at the very beginning, we had sliding window semantics, which is a very stream native operation on stream computation. Then, of course, came the idea of doing task parallel execution, which is what most modern stream processors are doing nowadays. And then I have two of my favorite features on Flink, especially state management, the idea that you have explicit state and the system manages things like fault tolerance or reconfiguration, as well as out-of-order processing, the idea of doing computation incrementally and triggering it using watermarks. And that's where we are today, I think. We've seen two very nice things today in the keynotes. One was the idea of doing cross-key transactions, and the other was the integration of batch and streaming. And what I would like to present today is something that is a bit complementary to both of these. And it comes under the fancy name of arbitrary computational nesting. I would say what simply this principle is basically something we need to do structured programming on data streaming, as well as supporting things like structured iterations. So has streaming really subsumed batch? Short answer, no. And that's due to the simple case that in streaming, in the streaming runtime, we cannot do multipass computation. So the batch runtime on Flink is using datasets, which are doing staged processing. And there is support for bulk and anti-iterative computation. While on streaming, we have something like a continuous stream of data, and the application is something like a single pass pipeline, where we do continuous processing, and that allows correct processing only for acyclic computation. So right now on Flink streaming, if you try to combine iterations, which is an experimental feature, with event time windows, this will not really work out. There will be a warning that this is not really supported. So can we have a model that combines those two? And that is the question I'm trying to answer. And first of all, let's see why iterations matter, why they're important. So iterations are fundamental building blocks for many types of analytics. For example, graph analytics, algorithms such as PageRank, connect components, single source order paths, and so on, are based on iterative computation on the bulk synchronous model. Machine learning algorithms, those who work on machine learning know that most of the important deep learning algorithms and deep machine learning algorithms are based on iterations. For example, Stochastic Gradient Descent, principal component analysis, and all of these are, by definition, iterative. Also, we saw transactions in the morning, multi-key transactions. They are, in fact, operations that require iterative processing, a form of feedback loop. And all of these are needed, yet they are not currently supported by state-of-the-art production-grade stream processing systems today. And there are many challenges, especially for those who work on those fields, because data is born and evolves continuously as a data stream. We have data coming as user interactions, sensor events, server logs. They all create a continuous stream of data. And what data analysts do today is that they bucket that data into buckets, like let's say daily data, daily logs, or monthly logs. And then they try to run their iterative model building algorithms on top of those batches, or those buckets. And then comes the ugly part, where they have to sort out the results of the computation and try to merge all these models together and sort out what they can use in production, let's say. This is a lot of clumping, and it's not really, it's an anti-paradigm when it comes to streaming, Because what we know so far is that most of these problems can be solved already using window computation, right? So most of these challenges I mentioned are automated in a single pass, at least using windows. So windows are, in fact, a natural fit for declaring iterative computation. So the question here is, how would the distributed iterative computation look like as a special type of window aggregation? So I'm talking first about semantics here. If we try to model an iterative computation, it looks a bit like this. This is the most abstract way I can define iterative computation. So we have, first of all, a solution that is defined as finite state. And then we have computation defined as a loop step function that takes our solution and updates it stepwise until we reach a final result. There's also a termination condition that defines when we actually stop running the step function. That can be, in distributed computing, this is either fixed point on the solution or fixed on the number of iterations. And in the end, we have a final result. Let's say this is a very general abstract model of an iterative computation. Now, what we propose is a way to, is an extension of the data stream model as an addition to the existing single-pass window aggregation that instead does multi-pass aggregation. And we can also do other things on top, like DSLs, for example, doing graph, purgeable computation on Windows, and so on. I'll just briefly explain how this API would look like. We have an implementation for those who are interested. This is still a research project. So we define a window, key by key. We define a window, and then we run an iteration. An iteration consists of, first of all, a termination criterion. Currently, we support natively fixed point or fixed termination. Synchronization, which is very important. How we want our parallel task instances to synchronize the step computation. As you know, like the bulk synchronous model adopts a strict synchronization model. Otherwise, you can also allow some kind of staleness across parallel tasks. And this is described as a stale synchrony. Then there's a key by which we partition our iterative computation, and three main functions that do the aggregation: an entry function that initializes the state of the iterative computation, a step function that runs the step on the state, and a finalize function that outputs the final result. All of these run per window basis, right? And there's also a context associated with this operator. So the important thing is that you can always know the local progress, the local step of the computation, the global step, which is the last parallel complete superstep, the current event time of the window that triggered the computation, and also define state, two flavors of state. One, as you know from the single pass aggregation, it's the same thing. Loop state defines state that is purgeable per window, and persistent state is the global state that persists across windows. I'll very briefly show an example because I don't have much time. We define a window. In this example, we have edges, a stream of edges, and we want to run PageRank. You know PageRank, it's a very simple algorithm. It's defined by this function based on the size of a vertex and a sum of the output edges. So when we define, in this example, iteration, we want to run it, for example, in 40 parallel supersteps. We want strict synchronization. And then in the entry function, what we do is that we, first of all, get the contents of the window and define, initialize our state. In this case, our state is basically the list of neighbors that we use to run the algorithm. That is, of course, keyed by vertex. Then we have we initialize the ranks. In case we have stored a previous rank for the same vertex from a previous window, we can always fetch it from the persistent state. And then we start the algorithm by outputting, collecting the initial ranks. You know the step function, it's very trivial. We collect all the ranks from the neighbors, and then we define a new rank and send it to our neighbors. And that repeats for 40 times per task. In a synchronous way. In the finalize function, we get the last rank, and we collect it in the output. That's a very simple example. Of course, we can do more fancy things, like defining DSLs, like the purgeable on Flink. This is how this would look like. I won't get into details. So I'll talk about something more important. So enough about what, let's see how to do all these things. So we know that windows are executed in parallel and out of order based on event time progress. What is event time progress? I would say event time progress is something like a logical clock that sits on every stream task. And that clock gives an indication of a low event time bound. What this means is that for every input record that arrives in a task with a timestamp t, this timestamp is guaranteed to be above or equal to the progress metric of the task. And t can always increment monotonically. That's what defines event time progress. And of course, the way it's implemented, as you know, is through low watermarks, with a decentralized, very simple algorithm that actually works. The idea is that the tasks disseminate from the source to the sinks their local progress metric, and then each task derives its local progress metric as the minimum across all the watermarks it receives. So its progress metric sent is a watermark. It's called watermark. And that works correctly as long as monotonicity is maintained, which is trivial in a cyclic graph. Now, iteration supersteps and event time progress have many things in common, right? They can be both used to run computation in out-of-order streams. They both need a decentralized mechanism, no coordinator, and those metrics are both only relevant to the respective parts of the graph where they are needed. For example, sources do not need to know about the sync progress. Currently, of course, as I mentioned, it's not possible to combine cycles and watermarks. Why is that? It's because Flink currently allows arbitrary cycles. It means that you can define any cycle in the graph, and that means that if watermarks would propagate through those cycles, they would have no meaning. They would violate the progress metric guarantees. For example, when you send a watermark back, you send an old watermark, which is something that already violates the assumption. Then tasks don't know in which cycle they belong, and the records are not associated with a specific cycle or iteration. So it's a very complex thing that cannot be done in an arbitrary way. We need a structured programming primitives to implement that. So what we propose is a way to do structured programming on streaming, and that's done via structured loops, an abstraction that I'm going to define, progress timestamps, an extension of watermarks, and cyclic flow control. So structured loops, this is the core of the main idea. Structured loops are low-level stream graph primitives, and they can be seen from the outside as iterative operators, right, as one operator. So each structured loop has its own scope, lexical scope. You can think of lexical scope in programming. And its scope operates on its own progress metric that they can only see. The global scope, as you know from vanilla Flink, in an acyclic graph, operates on event time progress. We don't change anything there. What changes is, the changes that happen are inside the structured loop. A structured loop embeds a full computational graph. You can think of another computational graph inside an operator. And it has some restrictions. So it has a predefined input stream, a predefined output stream, and a native feedback edge inside. Of course, it has its own scope, and each operator in that graph, inside the structure loop, can its own be another structure loop. So we can have what is called arbitrary nesting in streaming. That's a very important property from programming languages that allows you to encapsulate computation at different levels and hiding the complexities. Of course, watermarks have to change to work with this model. And times in general, the notion of time. So instead of times and timestamps, we talk about arrays of times. So this is what we call progress timestamps. And the progress timestamp looks like this. The first time is the time of the scope where it's inspected, and the rest is called the context. Okay. Progress timestamps support some operations like what's the current progress? That's a head, a nest. So basically removing the head, nest, adding a head operator, and also incrementing the head. Okay. So how all these things work together? we actually embedded some special operators in a structural loop that actually do all these things automatically. So what happens when a record or a watermark enters a structural loop is that an input operator, it's like hidden from the user, initializes the scope progress metric. So what it does effectively is that it takes every timestamp and nests a new progress metric initialized in 0. Okay, so 32 would become 0.32. That goes into the graph. Whatever goes out of the structural loop is unnested. It means that we remove the head of the timestamp. So basically, the local progress is not visible outside the structural loop this way. Whatever goes back, as you know, Flink currently has a head and a tail operator when you define an iteration. The tail operator in that case increments every progress metric by 1 automatically. And then the head operator forwards records and watermarks, and then also runs termination criteria that disseminates termination about the context so that we can do garbage collection. This is how the managed state operator, the multipass window aggregation operator looks like if we embed it in this model. So it's basically one operator that works out of the box using these abstractions. And we can also use the progress timestamps and the progress metrics to do synchronization and run this correctly in parallel. What keeps us busy currently, I would say, is cyclic flow control. And that's where I would use the community's advice. There's already a flip about this in Flink. So we want basically to avoid deadlocks and encourage iteration completion. And also state management is not as trivial because we have one more level of indirection, not just state per key, but we have state per key per loop. Currently, we try to do flow control between the input stream and the feedback stream, so we can prioritize the feedback stream when number of consumed buffers is elapsed. And I would like to bring your attention to this flip 15, where the internals of these principles are introduced. So this flip defines scoping and nesting, and also discusses flow control alternatives. So if you really like iterations and you want them natively supported on streaming, I would encourage you to start a discussion on this flip, since it has been inactive for a while. These are the members that have directly or indirectly helped in this project. First of all, Marius, who has been a master student working in this project. He has also done some interesting performance comparisons with Naiad, a very similar system. Asterios, Vasya from EDH, Safe, my advisor, and Pramod, Marius' advisor. So we have all worked together in some sense to define all these things. If you want a very clear formal specification of what I explained, since that was a very short talk, you can read my PhD thesis, which is called Scalable and Reliable Data Stream Processing. You can find it on the web, or you can ask me if you can find it. And also, these references, if you want to get more insights. And I'm up for questions.
Are there any questions from the audience?
Thanks, a great talk. You quickly mentioned it at the end of the presentation, but indeed it really looked like Naiad and the timely streaming, I think.
Timely data flow.
Exactly. So is it fair to say that this is what you try to implement here?
It's slightly different. I would briefly say that the main difference is that Flink has a more decentralized execution model, which means that the state can only be local to every task. There's no external state. In Naiad, in timely data flow, there is some sort of scheduler that runs centrally per task, per node, the progress tracking data structure. So this scheduler actually derives what's the global progress and then notifies the tasks. This we cannot do on Flink because we can't have state that lives outside the tasks. That would not be consistent and fault tolerant. So we have to comply with watermarking and decentralized mechanisms.
Okay.
Hi, nice talk.
Thanks.
I know you mentioned in the end that you still have to look for deadlocks, but the first thing I thought when I saw loops and arbitrary nesting was, how can these always terminate, right? And I spot that the restriction on the domains for the time to n might have something related to that, but can you say a little more on this side? What? Speculate if you don't have an answer.
Regarding termination of the iteration computation, that is something that the API enforces in a way that you have to select between fixed point and fixed termination. Okay. If you don't reach a fixed point, yeah, the computation will run forever. But the algorithms, yeah, that's the point, right? You might want that also.
True.
Could you talk a bit more about the differences between the centralized progress tracking and the distributed progress tracking? What are the advantages?
Wow. Yeah, that's a complex question. So centralized, you mean naiads? Or?
Yes, yes.
I wouldn't say it's centralized, first of all. So naiad has a node parallel progress tracking mechanism where they run data structure called undit chain that collects basically, that sits between the network channels of all the nodes. Naiad has a slightly different execution model, as I said. So the computational graph runs as is on every node. It's not task parallel, it's more like node parallel, okay? So what happens in Naiad is that this tracker intercedes all the records that go between nodes and channels. And then you can use this data to infer what's the progress from the timestamps that are inside all the records. While on Flink, we cannot do that because there's nothing sitting between all the network channels. We have to run the progress tracking computation internally on every task. I don't know if that's clear. So that's why we have to go with watermarks in this case. It is more decentralized, if I can say so. But Naiad has an interesting model as well.
Okay, thank you.
It's just a different execution.
Thanks, everyone. We're breaking out, and there's a follow-up session in 5 to 10 minutes here. Thank you very much, Paris.